Let me make sure the link is working.
Yeah. It's like everyone.
I think it's
Because it's really good. Yeah.
I like the chalk that they use in MIT videos.
Oh,
Like the big fat
yeah.
ones.
my channels. Right now.
I don't know. Okay, that's pretty cool.
Yeah, let me just update the link to Piazza. It's annoying because every time I go live, the link changes. It's updated. Okay. Could someone help me monitor the Piazza or the live stream to see if it works for everyone? Okay, update it again. Okay. So I assume this link works. Yeah, it's live. Cool. So let's just monitor from here. Let's start. And do you know if the sound works okay on the stream website? Can you hear the sound from the laptop if you open this website? Alright, so let's just assume everything works. And if they complain it, we will set it up again. So thanks for coming. It's a larger group than it usually is. The plan of today's problem session is to help you start with PyTorch. So I will introduce all the basic concepts about PyTorch. First of all, how many of you have heard of or have coded with PyTorch before? None of you? Okay, that's nice, because then I have something to talk about. So I assume all of you have heard of TensorFlow, right? Have you heard of TensorFlow? Okay, I saw some people nodded their heads. So TensorFlow is developed by Google. So it's a deep learning framework to create models, train models, and deploy models for any kind of prediction tasks. Mostly about deep learning models on NLP, vision, or some other problems. And PyTorch was developed by Facebook. It's also an open source project, so it has the same features or functionalities as TensorFlow. But it becomes very popular recently because it's very easy to learn this framework compared to TensorFlow. But of course, TensorFlow is getting easier. But I think, that's my personal opinion, PyTorch is still much easier to learn if it's your first time building a deep learning model. And a lot of people agreed on that. So just for the convenience of learning, we will introduce PyTorch in this course. And if you have never learned any deep learning frameworks before, you can use PyTorch to do homework 5. I hope that's enough about PyTorch. Any questions about PyTorch, or should I say more about PyTorch?
What's the difference between just a deep learning model and like a ANN or CNN?
So ANN is artificial neural network. CNN is convolutional neural network. I think ANN is a very vague term. I don't hear anyone say ANN normally.
But so like we've learned that, saying like what's the difference between what we've learned and a deep learning model?
Yes. Let's see. So we usually call all neural network-based models deep learning models, simply because even if it's only 2 layers, we still call it deep learning because it's deeper than 1 layer. Because logistic regression is 1 layer, so if it's more than 1 layer, we'll call it a deep neural network. And have you learned convolutional neural network in the past lecture? Okay.
What?
Convolutional neural network is CNN. That can go as deep as 200 layers from what I've seen before. and they are very effective at image classification, some kind of visual recognition tasks. And if we are talking about text or recurrent neural network models, have you heard of recurrent neural network? Heard of? Yeah. So that's more applied in text problems, and Google has also built some models that is higher than 12 layers of recurrent neural networks. So back to the question, what's the difference between ANN and deep learning models? They are the same thing, I think. It's just different way of naming it. All different. There are a lot of different neural architectures people worked on, and you can call all of those models deep learning models, and you can build those models with PyTorch. So I believe you've worked on building a neural network by yourself in the last homework. So it's a lot of work a lot of coding to make it work. But if you start with an existing framework like PyTorch, it's very few lines of code, because it takes care of all the training, all the inference tasks for you. So what you do is you just define the model, the parameters in the model, and then you feed the training data. It will automatically train everything for you. So they provide all the optimization techniques for you to optimize this model. So you only need to define the model, but you don't have to worry about how to optimize it, how to do back propagation, things like that. So let's see. You can find a lot of materials about PyTorch in the website. There are a lot of good tutorials. To finish this assignment, I believe you only have to read very little of them, and then you can make homework 5 work. Or if you just finish this tutorial, I think you can almost finish homework 5.
Does PyTorch have a convolutional network library?
Yes, it has.
Use that for question
yes,
class
you can use that.
Is
So
that kind of like cheating, just telling you how many layers you want, and then we're done?
yeah. I think the idea is just to get you familiar with the deep learning framework, because there is a question in homework 5 that asks you to code it yourself. So in that particular question, I believe you can't. But I don't know if the professor has removed that question or not. At least in the past course, in the last years when there was this question. So you will be able to see all the so they do have those convolutional neural network frameworks. So it's not you still have to specify something, but it will be very little amount of work. But in homework 5, we have a pretty big data set, about 1 gigabyte. So even if you set up everything, it still takes a while to finish training. We should be able to provide you some GPU resources from RCC. So it's a good opportunity to learn how to train it on GPUs. Now let's get back to the basics of PyTorch. So PyTorch, you will find the syntax of PyTorch very similar to NumPy, and even TensorFlow is very similar to NumPy. It's just they built it this way so that people with knowledge of NumPy can easily learn PyTorch or TensorFlow. But the difference between NumPy is that NumPy has a lot of the basic unit of NumPys are those ND arrays, and these are just matrices or higher dimensional matrices called tensors. But in PyTorch, an ND array or a tensor is more like a computational unit in a computational graph. Because if you've learned those neural networks, you know there are a lot of nodes in them, and each layer is like a tensor, and the tensor is with some linear or nonlinear transformations, it goes to the next layer. So these are just tensors in each layer. And when you do back propagation, each tensor will get some kind of gradient associated with this tensor. And when you do optimization, you want to update the parameters of the network by the gradient. So it's like with PyTorch, each tensor here is not only a tensor, it also has the gradient associated with it when you are training it. But you didn't observe it when you first use this framework. And after you define a neural network, PyTorch provides a lot of tools to train the model. I'll just quickly go through this tutorial with you guys. So you first import torch, and let's see the version of this torch. The torch of this torch version. It's 1.0 and 0. I believe there's an updated version, but I think it didn't change too much. So if you want to initialize a tensor, you can do torch.empty. But normally people don't do that because it's uninitialized tensor, so whatever in the memory will be there. So those numbers are very weird if you check them. And rand give you a random tensor of shape 5 times 3, just like NumPy. So it's instead of seeing an array here, it's a tensor, but it's a PyTorch tensor. If you check the type of x, you'll find it's torch.tensor, and you can get the shape by x.shape. It will give you a size, and if you want to get a particular dimension, you just get that dimension. It's 5 and 1. And torch.zeros will give you 0 tensors. And this D-type is similar to NumPy's D-type. There are long types, there are floating arrays. There are also double, things like that. And you can initialize a tensor by passing a list, or you can, so these are ones array. So this new one's a 5 times 3 array with type double. And the random like gives you a tensor with the same shape as the first parameter. So x is of shape 5 times 3. So the second x here will also be of shape 5 times 3, but it's randomly initialized with data type floating type. And x.size is the same as x.shape. So it will give you a tuple.
Wait, why did you say x.newOnes and not torch.newOnes?
Oh yeah, I forgot to mention that. So x.newOnes means you will create an array with the same shape as x.
But then you give it the shape anyway?
Oh yeah.
5, 3?
That's a good question. So I believe if you delete that, let me just do that again. x.newOnes. Let's see what it does. 5 times 3. So I believe it should keep all the properties of x, like the data types. Yeah. Right. Yeah. So, but anyway, I think people usually don't initialize it this way. A lot of times you initialize from a NumPy array. Did I mention anything about NumPy array? Let me just first go through that, and then if there's anything missing, I will talk about that. So operations, if you have two arrays, x and y, you can do element-wise addition. Okay, I believe the shape is wrong. 5 times 3, rand 5, 3. Okay, so if you have two tensors of the same shape, then you can do that. And all those broadcasting rules in NumPy still applies in PyTorch. So if you forget that, just check how that works in NumPy. Just quickly speaking that, if all the dimensions match, you can do element-wise operation. If one dimension is 1, then it will be expanded to the other tensor's dimension, and you still do element-wise operation. And you can also use .add. It's the same, just different syntax. And you can specify the result by this out parameter. I usually don't do that. I believe the reason why you want to do it is it might save some memory in some cases, so you don't create a new tensor. If you already have a tensor result, and you want to save the result into that tensor, then you can specify it that way. Yeah.
So someone who's following online says he can't see your screen.
So
He
why?
can't see any code.
Oh, let me see. Is there another screen somewhere? So can you see the code?
Maybe rerun out this.
That's strange. Do you guys know how to fix that?
Yeah,
Why?
if you click on your Apple
Oh, I click this apple.
display, yeah.
Mirror, I guess. In the right place.
Lock screen.
System preference.
System preferences. Oh, just displays?
And check mirror. And arrangement.
In, let's see, arrangement. Okay, I think it's already mirrored.
Yes. Nice.
It's in this screen. That's very strange. Do I?
You move to another screen. You guys know how to move between screens?
Oh, I think that's because I have to set it here. Okay, it is weird.
It says display capture, right?
Display capture.
Stop streaming in this.
Audio's right, because I can hear you.
Okay.
Maybe click the settings of that on the bottom.
Input videos. I don't even know where this screen comes from.
I think you have to stop streaming first.
Okay, now let me go to my live dashboard. It should be live again.
Yeah, that's live. That's live. It's looking at your screen.
So I think the link has changed, so I have to get my link again.
I'm on it now. I can see your. I can see that.
Oh, you can see it
I can see that.
in your laptop.
Me too. Yeah, I can see you.
That's cool.
If you
Just
can open
to-
up the notebook now, it'll probably work.
Just to make sure that it's still the correct link. So is it like this? Video unavailable.
A little behind.
Was that the... I think that's the previous video.
No, it's correct.
Is this the current live stream? That is the current stream, I believe.
But then it's on Piazza.
Yeah, if you open up the notebook, I think it's good.
Let me just post that again.
That link, that's the right one. That's the one I'm using.
Oh, okay.
Yeah.
Cool. Now let's go back to this notebook. So why add? So everything with this operation name and underscore means in-place operation. So y add x means y plus x and store it back to the memory of y. Okay, cool. Thank you. And you can do all those advanced indexing, like similar as NumPy. This y get everything on the first dimension and get the first element. It's actually the second element on the second dimension. And so NumPy, if you want to reshape a tensor or reshape an ND array in NumPy, it's called reshape. But in Torch, it's called view. So if you have a tensor of shape 4 times 4, you can say x.view16, and it will be a flat array. And -1 means automatically calculates the dimension of that, the length of that dimension, and so it will become shape 2 times 8. And if you have a tensor with only one element, you can use .item to convert that to be a NumPy number. That is usually used when you calculate the loss, because the loss is usually a tensor of only one element. Then you can use dot item to directly get that item. Because if you don't do dot item, then when you print it, it has a lot of those noisy information like tensor parentheses. But if you get the item, you get the number directly. And there's also the problem of, I think the annoying part is when you are training on GPU, you have to, I should talk about that later, but you have to move all the tensors into your GPU memory and then do the computation there. You have to make sure all your model parameters and all the tensors involved in the computation are in the same GPU, and then you can do the computation. Otherwise, you will get some errors, like it's expecting a CUDA array, but you have a CPU array. If you see that error message, it means you have to move that to a GPU first.
What's a CUDA?
CUDA is a library from NVIDIA, because you know NVIDIA produces all those good GPUs, and they have their own library called CUDA to handle the matrix, those scientific computations on GPUs. So they have so NVIDIA has CUDA library. So if you want to do deep learning directly with CUDA, you can also do that. I believe there are libraries who most of them are written in C or C++, and they directly talks to the CUDA library. And they also developed cuDNN, which is a CUDA version of deep neural network library. And I think there's some other middle layer in between. And then finally it's PyTorch. So PyTorch, there are a lot of layers to go all the way to CUDA computation. So the most commonly you get the tensors from a NumPy ND array, and then you want to convert that to a tensor. So if you have a first if you have a torch tensor, then you can convert that to a NumPy array by simply calling .numpy. Why do you want to convert that? It's useful in a lot of the cases. Let's just leave it there. When you want to convert a torch tensor to a NumPy, or what?
You want to graph it or something?
Oh yeah, sure. Yeah, if you want to use matplotlib to plot it, or because when you want to do a lot of things with Python, it's easier to work with NumPy than with PyTorch. So here's a bridge between NumPy and PyTorch. And what's interesting is that they share the same memory. So now B and A are both of value 1s, and if you add 1 to A, the value of B also changes. So B just maps to the same memory place. And if you want to convert a NumPy ND array to a torch tensor, you just do torch.numpy and a NumPy ND array. So then you get another torch version of the same NumPy ND array. And again, they share the same memory location. CUDA tensor, I won't be able to demonstrate that, but if you have a CUDA device on your machine, then you will see torch.cuda.isAvailable becomes true. In my case, it should be false because this is just a laptop. I don't have a CUDA. I don't have a GPU here. But if you have that, then you can set device to be torch device CUDA. People usually write it in this way: device equal to torch.device CUDA if torch.CUDA is available, else CPU. So it's either on CUDA or on CPU. So in my case, my device will be type CPU. So it should do all the computation on my GPU device. And it's a good practice whenever you create a tensor. If it's going to be used later in computation, you set it .toDevice. So x.toDevice means move the current tensor to my destination device. If it's CPU, then it doesn't do anything because by default it's on the CPU. But if it's on CUDA, if device is CUDA, then it will be moved to CUDA. And you should do the same thing to your model later. If you define a model, you can move the whole model to your device. So it basically means move all the parameters in the model to that device, because a model is just a combination of all the weights and parameters you have.
What does a ones underscore like mean?
It means create a tensor of all value ones, like the shape of X, and also the data types.
So it could be similar to X1's
New ones,
device.
new ones, yes.
New ones.
Yeah, there are a lot of ways to initialize that. You can take a look from the documentation, how to initialize everything. So these are all about the tensors. Any question about the tensors in PyTorch? You'll find the syntax all very similar to NumPy, except it has two different device versions.
So in class we talked about tensors being like is it like n height, width, and depth, right? Like number of elements in the tensor. Like for example, a tensor of a filter was like number of filters,
Yes.
height of the filters, weight
Yes.
of the filters,
Yes.
and depth of the filters. It was always
Yes.
4 numbers.
Not necessarily. That's just it's a particular case in convolutional neural network. A tensor is just an ND array of any dimension.
Okay, so
It doesn't have to be
significance of the
rankful.
places being particularly, because in this case it's like a function, right? Like it would take number of filters, height, width of filters, and depth of filters, so that it could do like operations. That is a definition that's more textbook than software, right? So in this case, this is just an array with more dimensions.
Yeah, a tensor is just an array with more dimensions. It doesn't have to be any particular shape.
Okay. And then you said that you would think about it as like on each layer there was a tensor.
On each layer,
So,
so in the case of multi-layer perceptron or the artificial neural network that we implemented in homework 4, you can think about each layer is a tensor. It's just a matrix of 2 dimensions, because it's Wx plus b. W is a 2D array, and b is a 1D array, right?
So in homework 4, so we have nodes. We have a theta
Yeah.
matrix that multiplies to the next layer. We
Yeah.
have more nodes. We have theta, right?
To the next
matrix
layer.
To the next layer. And
Yeah.
then we'll have deltas of k and deltas of each layer, which is like the back propagation of the.
So in the let's not talk about back propagation first. If you just talk about forward pass,
Yes.
then in each layer it's an affine transformation of Wx plus b, right?
Sure, for every
Wx plus b, right?
for every node.
Yeah, so W and B are 2 tensors here you want to define in the... Actually, they are all tensors. You want to define everything here. But I believe W is a 2-dimensional array. And X is a matrix, also usually 2-dimensional. And B is just a 1D bias vector, which is a 1D array, a 1D tensor question.
Is there an issue of just doing all the creation and then like sticking it in GPU and then send the like result out to CPU and then do whatever you need to do at the end? Because like I'm just curious, like is that doable? Like
You can do that, but what is the... I don't get what is the... Why do you ask this question?
well, I don't know, because it seems complicated. It's like why don't just do it all in GPU and then toss it out?
Oh, you can do that. You can definitely get everything to GPU, because those are just getting you familiar with all the syntax with PyTorch. We are not doing anything yet. They are not meaningful operations, I think.
Okay, so I guess one question is when we're doing a convolutional neural network, we will have like each filter will be on the same level, but they're pointing at different. What's the name of the zone?
Are you talking about local receptive field?
The receptive fields, yes. They'll be talking about different receptive
Yeah.
fields. Is that a different tensor then? Like
They are the same tensor. The same tensor applying on different local receptive fields. Because a convolution operation, if we just go to the
clones of the same kind of
Yeah.
size of tensor, but they're different tensors, right?
yeah, they are the same tensor applied into different fields. I would put it this way.
Okay.
So
They
when
have
you
their own local results,
yeah
which
they
make them different.
yeah so there are differences with parameters and your data. So the parameters are everything included in the model. Like all those filters you talked about, they are parameters of the model. And you have an image, those are your data input. And you want to apply your filter into different local receptive fields in the image. And they will produce the results in the next level. And maybe you want to do some other pooling operation or convolution operation to get further results. So the parameters are shared, they are tied into different positions. Does that make sense? Yeah. Okay, so now let's move on to how to create a two-layer neural network with PyTorch. You've done that by yourself. Why are you not agreeing? This doesn't work in your okay. But this with PyTorch is gonna be very simple. Let's do it step by step. Let's see what we are doing. We are working on. Let me copy this out. So we are trying to build a two-layer neural network, or two-layer multi-layer perceptron, or two-layer ANN. There are many ways to call it. So let's first set the hyperparameters. We have n. It's the number of training instances, and din is the input dimension. So your input is a 1,000 dimensional vector, and you have 64 vectors. And h is the hidden state, is the hidden size in this neural network, and d out is the output dimension. And let's first create some random vectors for this project. Let's see, x will be a tensor. You can check the shape by, so it's 64 times 1,000, and y dot shape is 64 times 10. And our goal is to create a function which maps x to y, and we will do it by MSE loss. It's minimum squared loss, minimum squared error. So this problem with this model is essentially a way to do regression or multi-factor regression. I don't know what's the best way to call it, but you want to map x to y by a two-layer neural network, and you want to minimize the mean squared error. So the distance between your prediction and y should be as little as possible by mean squared error, or L2 loss. There are many ways to call it.
You define your activation functions.
Yeah. So to define a model, you can simply do model equal to this torch NN sequential means a sequence of layers. Really? I think it will be back. Maybe the network was not good.
Oh, it's okay.
Okay. Now you define a sequence of operations with a linear layer. So it's a linear layer from d in 1,000 to 100, and then it's a ReLU activation function. You still remember ReLU, right? ReLU is the max of 0 and x. And yeah, and what's nice about ReLU is that if it would pass, the gradient is either 0 or 1. If the input is less than 0, gradient will be 0. If it's greater than 0, then the gradient will be 1. And you'll see why it's a good activation function later, in the later courses. And finally, it's a linear layer to map a 100-dimensional vector to 10 dimension. Now you can imagine if I define this model, you can directly check what this model is. It's a sequence of operations of linear, ReLU, and linear. And let's just get the first layer. This is a linear layer. And this linear layer has all those parameters initialized. So model 1 is a linear layer. It has weights. Is it weight or weights? Okay, those are the weights. And if you check the shape, it's 100 times 1,000. It converts a 1,000 dimensional vector to a 100 dimensional vector. So it's just a linear operation. It's matrix multiplication. So what it does is your input is a 1,000 dimensional vector, and then you want to multiply a matrix of 100 times 1,000. So 100 times 1,000 matrix times 1,000 vector gives you a vector of 100. And there's another parameter called bias. If you check the bias shape, it's 100. So this is how you do Wx plus b. And model 1 will be a ReLU activation layer. So that's standard. Model 2 is another linear transformation from 100 to 10. It also has those two parameters, weight. If you check the weight shape, it's 10 times 100. If you check bias, it's just 10. So these are all the parameters in this model. And you can also get all the parameters by model parameters. It's a generator. Let's see, if you convert that to a list, it will give you all the parameters in this model. So training such a model means optimizing those parameters. And currently all those parameters are randomly initialized. I don't know how they are initialized, but you can apply model to your data x. If you do model x, so you know x dot shape, x is of shape 64 times 1,000. And if you do model x, if you apply model to x, it does this two-layer neural network thing to your input, and then you get the output. These are the predictions. But currently, the predictions will be very bad. If you just do model x minus y, and we care about the L2 loss or mean squared loss. Mean squared loss is just you first square them and you sum them up, and you want to divide it by the number of instances, so it's just n. And this should be your, let me see, is that right?
The one that you used in the homework was mean.
It's this number. And we can define a loss function by so you define a loss function. And we define a loss function, because now let's recall what you need to do to optimize a model. You define some kind of loss function. In this case, it's a mean squared error. So the way it works is you apply the model and you take the input and you make prediction based on the input and your current model parameter. You have the output, and you compare your output to the golden standard, the optimal output, which is y, and you compute a loss based on it. The loss should be a positive number. It has to be positive or 0. And you want to minimize the loss as much as possible by optimizing the model parameters. And the way you optimize it is by computing the gradient of the model parameters with respect to the loss. And then you have this gradient. It's done by backpropagation. It's just a chain derivatives of the parameters. And after you get the gradients, you do optimization by stochastic gradient descent. So it's the parameters minus the gradient times a reasonable learning rate. There are different ways to do optimization. A standard way is stochastic gradient descent. There are other momentum methods. I usually use Atom when I optimize something. I just find it always works pretty well. all the parameters they have default parameters set in PyTorch. So if you don't pass a learning rate, it will use 1 to the power of -3, but I'm setting it to 1 to the power of -4. Usually you don't want to set a very big learning rate, because if the learning rate is too big, it cannot be optimized well. But if the learning rate is too small, then it converges very slowly. But if time is not a problem, that will still work. It will finally converge to somewhere. If the learning rate is too big, it will almost never converge to your optimal position. So let's just accept this setting. You have the loss function. This is the MSE loss. It's essentially doing what I'm doing here. But I set reduction to sum. So it should not be a mean squared error average. It means the mean squared error summed up over all the training instances. But that's the same thing. Optimizing that is the same as optimizing the average. And our optimizer is when you have all the gradient and your model parameters. How do you want to update the model parameters? If it's SGD, then it's minus gradient times learning rate. If it's Adam, then there are some momentum terms taken into consideration. So let's not worry about the details, because PyTorch takes care of everything for us. So you just have this optimizer. And note that the optimizer takes the model parameters. And I've shown you the model parameters is a list of, it's an iterator of all the parameters in this model. They are the parameters of the first linear layer and the parameters of the second linear layer. Value doesn't have any parameters, so it's just those two layers. And you specify a learning rate. And then, after we set the optimizer, the loss function, the model parameters, now we can do model training. So to do model training, this template is pretty standard. Is everyone still with me? If you have any questions, I'd like to clarify that first before I proceed.
So just to make sure, so
yes.
The model x minus y
yes.
squared was very large
because the
back propagation was not done yet.
Right. We haven't optimized the model parameters yet. All those model parameters are randomly initialized. I just want to let you see how bad this model is currently. And after we optimize it, the model will be good.
How bad is that 0.9919?
We don't know yet, because those numbers, the absolute values doesn't matter. We have to compare it with the final results after optimization. Now this template, this training code is a very standard training loop. You will see something similar to this a lot. I think my screen is frozen. Am I using too much of my CPU? Now this is a very standard training loop. Let me first train it. Let me not train it. Okay. So the first loop is, because you only have 64 data points, it's a very small data set. So we should be able to overfit to this data set easily with a reasonable amount of time. So we will train 500 epochs. If you're trying to copy my code, I actually post everything on my GitHub, so you can download it from there later. So you have 500. We have 500 epochs. In each epoch, you wanna first make the forward pass. So model X gives you the predictions. And these predictions are not optimal, of course. You have to compare that to the real Y. So these are Y predictions. And the real Y, you're gonna make sure that Y pred and Y are as close as possible to each other. And the metric to estimate how close they are is by your loss function. And in our case, the loss function is the MSE loss. And I'm printing the loss term here, so we know the model is making progress. And then after you have the loss, you want to compute the gradient. So this line of code, optimizer.zeroGrad, means removing all the current gradient in the model. Because the optimizer is defined based on the model parameters. And every time you do backpropagation, the gradients are accumulated. So you want to zero them out from the last pass. Because in the last epoch, you might do some backpropagation, already some gradient in it. You want to clean that thing up. And then you do loss backward.
So I'm a little confused about that because of how it compares to our model. Maybe my question is
Yes.
later, but the point is like you go forward, right?
Yes.
And then you get to the last layer
Yes.
and you compute the difference between your predictions and y.
Yes.
And then based on that, you calculate the gradient.
Right.
And therefore you're going to be overriding the gradient every time anyway.
Yeah. So let's think about how you do it.
So you don't
'Cause
use the gradient in
yeah,
forward,
yeah.
right?
So I wish I can draw some visualization here. Let's see. So let me just explain it in this way. Think about a neural network. In every layer there are multiple neurons, and our goal is to compute the gradient of this node to the final loss. And there are multiple paths coming back to this particular node from the final loss term. And you will not override the gradient every time. You accumulate the gradient. Because if there are 3 paths, you want to sum those gradients up.
So the way I do it is I run a transform of the theta on the layer in front of it, and the addition is all done at once. And
I
it
see.
Definitely overrides it.
Okay, I see how you're doing it. That makes sense. So consider a more complicated case. If you have multiple losses, you don't have to only have one loss. You can define the models. You can define the model as complicated as you want. There could be some middle layers, and it will be.
I see what you're saying. So there's some cases in which I can't do it in one
right.
step.
Yeah.
Okay.
And
So I
you
have to zero it out when I'm done.
Yeah.
with my-
Right. So it's a safe choice to zero out everything. Maybe in some cases you don't have to zero it, but definitely not in PyTorch. You have to zero it, and then you do backward. Backward is the step of backpropagation where you compute all the gradients. And now after loss.backward, I think I should do it step by step so I can demonstrate what is happening here. So let's do y equal to ypred this, and we do loss function ypred y, and I should put it to loss. Now you have a loss. This loss is a very big number, and then now if you check model, let's find some particular parameters. So you can do model.parameters list. It's going to be a huge thing. And I want to find the gradient of all the parameters, p in these parameters. For p in model parameters, p.grad. You'll find they are all none, because initially it's all none. There are no gradients. And now let's use, so now you don't even have to do optimizer zero grad because there are no gradients. So let's just do loss.backward. Now if we check the gradient again, you'll find you have all those gradients. These are the gradients to all those model parameters. And they should have the same shape as, let's print the shapes. They should have the same shape as the model parameters. If you just check the shape of the parameters, they are the same. Because the gradient has to be the same as the parameter shape, otherwise you can't do parameter update. Does that make sense? And now the next step to do is, since you have all those gradient.
What's the shape of the parameters? Oh, and the gradients are also the same?
Yeah, the gradient and the parameters have the same shape. Because you will just think about how they're computed. They always have the same shape. And then after you have those parameters, you can do optimizer.step. That's the step of stochastic gradient descent. In our case, it's gradient descent with momentum. Okay, what's happening here? Let's do step. Now, if you now the gradient has been updated, but you will see that if we print the gradient, they are still there. So that's why in the next step we have to do zero grad. So if you don't do zero grad, let's see if we do. Now let's imagine we are in the next epoch. We make prediction again, and we compute the loss. And they are gradient already, but they are not the correct gradient because they are gradient from the last iteration. Now if you do loss dot backward, it still works, but the gradients are wrong because it's accumulated from the last one. And you'll see the gradients they should be different now. Let's just compare the first row. So you'll find the gradient almost doubles because the parameter hasn't been changed too much, so the gradient just doubles. And they are still of the same shape. You can still do optimizer.step, but you will find that's not ideal. If you print loss.item, you will.
You did calculate it again.
Yeah, so it's like you accumulated all the gradients. So that's why you should do
What's the shape of Y bread?
Y grad.
Y bread. The predictions.
Oh, yeah, it should be the same shape as Y. Y parad. Oh, sorry. Is that the same? Yeah, it's the same. 64 times 10. So it's the
So that
same
means you
shape.
went through all of the data set on one iteration T.
Yes. Because in this case, we only have 64 data points, so you can do that.
And that's
But
why
in
you're saying that the gradient is accumulated. Because like when
Yes.
we're doing stochastic, it's one example, not many. Right?
You do a portion of the entire data set that's mini batch. If you do one at a time, and then so you do one example and update the gradients and update your weights, that's stochastic. But so now I
Okay.
don't see, because the textbook, I don't know if the textbook is right or wrong anymore. It's such a lot of typos.
So this field has developed a lot recently. So you will see about 10,000 papers published, or about 10,000 papers published every year. So a book written 5 years ago, I would say it's an old textbook. I would imagine a lot of terminology might have changed. So what I've heard most often is, if you take one example, it's called stochastic gradient descent.
One example per epoch, right?
Not per epoch. I would say per iteration. An epoch is usually after you go through all those training data. It's called one epoch.
Yeah.
Let's
I
say
guess
if
the
you
difference would be updating the gradient after each example, or
Or-
updating
Right.
The full-
That's the important
yeah,
part.
yeah.
When do you update the weights? Do you
The-
update after every observation or after the whole?
A common practice is by batch gradient descent. You take a batch. Let's say you have 10,000 examples. You don't want to update your parameter after you see all those examples. You update your parameters after you see a batch of them. Let's say
It's called
32
mini
of them.
batch.
Yeah, it's a mini batch or batch.
No, because batch for us is everything. The 10,000,
Oh.
everything.
So you thought batch means
I
everything.
didn't think that's what they taught
That's
us.
what we've been told.
Literally.
Batch is everything.
Batch is using every example.
Okay. Yeah, okay. Now I see why there are some confusions.
This is batch gradient descent.
Well, this is
Okay.
not batch because he's using something else. He's using like
Mini
This is
batch.
no, he's using
500
atom as his optimizer. So he's doing something else. He's using momentum of whatever shenanigans.
Yeah.
Don't worry about it. But he's not doing gradient descent. He's doing something else.
Yeah, you can change that to SGD if you want to see how SGD performs. Let's do SGD and it's stochastic gradient descent. Then atom,
So
it's similar to
according
SGD.
us, if it were at SGD, I guess, well, that doesn't make sense, right? Because you're now predicting a Y that has 64 examples, and that's not stochastic, right? You've predicted all 64 of them before you've upgraded any gradients. So now for us, at least for what we know until now, you're going to calculate the loss function on all 64 examples.
Yeah,
And then you're going to optimize it.
yeah,
And then you're going to backpropagate it.
yeah, yeah.
And for us, that means you did full gradient descent.
Yes, in this case it's full gradient descent, but since the full is so small, it's only 64, it makes sense to do it.
Sure, but you call it SGD.
Oh, I see.
But you give it 64 examples anyway, and the
I see.
computer doesn't complain.
Right?
Yeah.
Now it's screwing with me because you put in
So
you
in
put in
the
SGD, but then you're calling
Okay.
loss backward
Yeah.
only once after you've gone through the whole thing.
Yeah.
It's like counterintuitive to what
Right.
SGD is.
Okay. So in the terminology of PyTorch, there is always batch size as the first dimension. You will always you will never do update after one example. You can still do that if you specify. So SGD doesn't mean you sample one and updates the parameters in PyTorch. It just means updates the parameters in gradient descent. I guess stochastic doesn't mean anything. There's no stochastic here.
You're killing me,
You-
man.
you've-
Stochastic doesn't mean anything. Jump out the window. Okay, maybe I'll believe that. I believe that it chooses some.
It didn't. It's always the full gradient of the particular mini batch. In our case, the mini batch is the full set. But you'll be able to see some other examples where you sample a mini batch and you do. So let's just assume SGD means that. But I do understand why you have this concern, because when I took the course, I think the definition is stochastics means one example, and batch or mini batch means take some of the from the full training set, and full gradient and full gradient descent means taking care of all the instances. Let's just if you understand that, I think that's fine. It's just a problem of terminology. You just follow the convention of what other people are doing. Now let's train this whole thing and see how it works. So you will see the loss decreases after you train it. It decreases very fast. It's only 500 iterations. Now let's evaluate the
What was T that you did?
key is it's iteration.
Okay, so you gave it 500.
Yeah, I'm just
Each time it went through all of them.
yes, yeah.
Okay.
So now let's compute the same thing again. Now you see model x minus y square mean is a very small number. So this model is, compared to the previous one, it's very good. But obviously it's overfitting to this training set. It may not be. These are just random noises. So it learns, it fits the noise perfectly here. Now we have, this is the whole workflow of how to build a model and define a loss function, define an optimizer, and do forward pass, backward pass, and gradient descent. These are, so I think that gives you almost all the knowledge to define a model. Now it's only a problem of making complicated models. In this case, our model is a very simple sequential model of 3 layers, but you can make it arbitrarily complicated. You can make it 200 layers, and I don't know how it performs in this particular problem. But in some vision problems, you can get a lot of advantage by defining very deep models.
Can we look at, like, even without making it that complicated, that many layers, can we talk about, like, giving X with depth? So, like, when we do images, we have, like, blue, green, and
Oh,
red,
you mean
right?
3 channels?
Yeah.
Yeah.
Can we see something like that?
Yes, I
Are we
will.
going to do that?
I will cover that in the.
You have 3 numbers, like one for layers.
Yeah. I will cover that later. But before that, let's just do another quick example to show how you solve a practical problem. Have you guys heard of the game of Fizzbuzz? So it's a very simple game. So you just count numbers 1, 2, 3, 4, 5, etc. Blah blah. Every time you see a multiple of 3, you say fizz. Every time you see a multiple of 5, you say buzz. And every time you see a multiple of 15, you say fizz buzz. So it's like 1, 2, fizz, 4, buzz, fizz, 7, 8, fizz, buzz, 11, fizz. Right?
Sounds like
13,
a tricky
14 FizzBuzz. So you just do that. So this game is, I think it's a nonlinear function mapping from digits to FizzBuzz. Or if you don't, if they are not multiples of 3, 5, or 15, then you just say the number. So you can code that with a, you can write a simple function to play this game, FizzBuzz. And let's write FizzBuzz decode, which takes a number I and make the prediction. So I have those two functions, maps I to fizz or buzz, or the number. And so let's try some examples. So 1 to 5 is buzz, 12 is fizz, 15 is fizz buzz. So that's a deterministic function to play this game. But we can also create a neural network to make such a prediction. It's a four-way classification, right? It's either fizz or buzz or fizz buzz or the original number. So it's a four-way classification. Now let's define, before we define the model, we first define the input and output. The input is the digit, and the output is 0 to 3, three different classes. We have defined those four classes here.
0 to 3, right? Because if you have to return I, then
Oh.
I changes constantly.
Yes, so we are just trying to categorize into 4 different categories. It's either fizz or buzz or the original number, fizz buzz. And
I guess what I'm saying is if the neural network is processing the whole data, at the end to do the output, it needs to know what the input was. It needs to save that along the way, right? Because like normally you're transforming that digit into signaling functions and signals, right? When you get to the end, you don't know what you started with. The last layer has no knowledge of the original layer. If you need to output it, you somehow need to like save it in a hash map or something so that you can access it.
okay, I guess that's too complicated. Let's just accept the current setting. You just take a number and classify it into 4 categories. And I'm going to do a little feature engineering here. I'm not going to input the raw digits. I'm going to convert it to its binary format. So the reason why I do it is it's easier for the model to train it. If you only input a digit, it's harder. If you input, in this case, I'm using 10 digits, so it can represent 2 to the power of 32 different. 2 to the power of 10, which is 1024. This number of digits. If it exceeds this range, then I can't handle it. This binary encode is a function to encode I to its binary representation. You should be able to understand that by yourself. And now we have training X and training Y. So these are the training data of X and Y in Torch Tensor. And I'm using numbers from 101 to 1024. Because I use 1 to 100 as my testing data, and I don't want to test and train to overlap. So I'm using 101 to 2 to the power of 10 as training, and the rest for testing. Let's check out train X. So if you check a particular example, train 0, let's see what this number is. Oh, I think it's in reverse order. So it should be 1100101. So this is 1 to the power of 0, 1, 2, 3, 4, 5, 6. So it's 64 plus 32, 96, plus 4, 100. So it's 101. And the next number will be 102, just things like that. And train Y will be 1. 0, 1. So 0 means the original number, and 102 means type 1. Type 1 is of a multiple of 3 and 3, things like that. These are the input and output, and our goal is to define a. Now let's define a model. We'll use the same model as before. Now the number of hidden is 100. Number of digits is 10. So it's a neural net. It's a 2-layer multilayer perceptron from dimension 10 to 100 and a ReLU activation, and from 100 to 4. This is the model we are working on. And the loss function, in this case, is cross-entropy loss. Do you guys know what a cross-entropy loss is? Sometimes it's called negative log likelihood. The way it's let me see, cross-entropy loss.
It's the Bernoulli log function.
Let me just, I think there should be some good examples online of cross-entropy loss. So cross-entropy loss is, let's think about the binary case. If you only have 0 and 1, then it's the binary log likelihood. So if it's 1, then you want to get the minus of log y hat. If it's 0, then you want to get the minus of the log of 1 minus y hat. This is binary cross-entropy loss. If it's multiple, if it's more than two categories, then it's a summation of this y is the correct label times the log of the prediction. So if it's a one hot prediction, meaning it's a categorical prediction, you're predicting a particular category, then the loss is minus log likelihood of that particular prediction of that category. So you want that to be as small as possible. Because, why? Let's see. You want your prediction of that category to be as big as possible.
Yes.
Then log of that has to be as big as possible. So minus of that has to be as small as possible. So it's because your prediction will be between 0 and 1, so it's always log of that is always going to be negative, and minus of that is always going to be positive. So you just want to minimize that term. Anyway, if you can't understand what that's doing, just think about the binary case. The binary case is simply the log likelihood of your particular class. Now we have cross-entropy loss, and the optimizer, this time we use SGD. It's just gradient descent. But the difference here is that now we are training 10,000 epochs, and since our training set is about 1,000 examples, we don't want to do gradient descent over the full data set. We will sample a batch. This time we are not even sampling, we just linearly get the batches. So the starting index is from 0 to the length of x, and the step size is batch size, and we get a batch. We get batch of x, batch of y, and we make a prediction based on our batch x, and we compare our y prediction to the correct batch y. Let me just write that. This is the forward pass. This is the compute the loss, and this is just 0 grad. You have to do that, and then this is backward pass, and finally it's gradient descent, model optimization. So that's how you will use this template a lot when you define a model in PyTorch. And finally, let's compute the loss of train X and train Y to compute the full loss after full epoch. Usually you won't do that. The reason is, so this is not a very good thing to do it, because train X and train Y could be big. A lot of time, if you directly apply it this way, you will get memory error. So a better way to do it is by, you can do total loss equal to loss.item times length of batch X, because the loss is averaged. So you want to multiply that by the number of instances. You can define total. Let's define total loss equal to 0, and you plus that, and then let's say loss is equal to total loss divided by what? Not batch size, the total number of instances. So it should be length of train x, right? Let's see what is the bug here. The size of tensor A4 must match dimension 1, and it comes from ypred and batch y. Oh, is that because I did not define that? Okay,
I still think
it works.
I still think that your loss has to be divided
By
length of
batch.
training x divided by batch size, right? Because the total loss is added only.
Oh, no. I see why you're asking this question. Because train of x is about 1,000,
Yeah.
and batch size is 128. So so if you observe what I'm doing here, this start will be 0, 128, and 256. It's not 0, 1, 2, 3. It's not going. It's going forward by a step size of 128.
Yeah. So
So
how many times did you go through this loop? You went through this loop 1,000 divided 128. Right?
no, it's just it should be 1,000 divided by 128.
That's what I'm saying. That's how many times you went through this loop.
Yes.
So if you
Are
want
you
to
saying
average your
Are you saying
total-
the length of this inner loop?
Yes.
It's about 8, right?
Whatever.
Yeah.
So 1,000
Yes.
divided 128. And then now you're saying you want to average your total loss. You want to average it over every time that you went through this loop. So it should be divided 8, not 1,000.
Oh, but I want to divide it over every instance. But anyway, it's more or less the same. It's just a number of scaling effect. If you observe the loss is decreasing, then that's fine.
Okay, that's loss per example.
Per example, yes. Because it's loss per example in the inner loop. I think we should take a break. Let's take a break of about 8 minutes and come back. Yeah, it takes a while to finish training. But you see the loss keeps decreasing. That's nice. What? Oh, let's see. I think it's a very random choice. You need to try. I usually use rabbit because people find it very useful in different tasks. I think it's also a little faster because the gradient is usually with Cambridge and Sigmoid, you have to do this kind of. Yeah. There's no. I don't have a theory behind it.
So when I tried training SK-learn from that model on the this data set,
Yeah.
and the rally did terrible.
Okay.
The sigmoid was like 90%. The rally was like 12%.
Okay. That's strange. I think there's some bugs in your code.
This was one line.
This is like a two line from
Okay.
top line.
I don't know. Or there might be some other reason behind it. But I think a common practice is if the neural network is very deep, you want to use that. If it's very shallow, it doesn't matter that much. If it's very deep, because there's gradients vanishing or there's gradients vanishing from value, it's either 0 or 1. So it won't vanish too much if it's 1. But if it's sigmoid, you have 1,000. If you have 100 layers, it could be very gradients could be very small.
No, this is
So is your server running?
yeah. Yeah.
So,
Where's your panel?
Yeah. The pen server code. Oh, I have to. It's under. It's under an. So I have to. Yeah. Yeah, it must be.
that was
Yeah.
Basically, like when you're saying response
Yeah.
based on whoever you're returning from the hand tools, that
Yeah.
that panel returns the
Yeah.
assets on the That's the thing. The response is those
Yeah.
Yeah, but it's just means it's people.
Oh.
When you do that,
It's.
so like,
but he's not using it, so
Yeah.
he wasn't using it.
but let's say your fault, like I said, it's
Yeah.
most recent.
Oh. Yeah. Yeah. Yeah.
Ryan, are you using Jupyter notebooks for your
Not sure. No, just say the base.
Are you using DSO? You can like run cells.
No. Just run it.
I switched over to Adam. It's like you
Add it. 100 to 1. That was you didn't run cells. I mean, I'm sure.
I don't even know if you trust to go not to, but it like will open it up.
200 to 1. 200 to 1. You can stand up too.
I just stand.
You can stand up.
Okay.
10 cents.
You're so-
I'll take give me 1 to 5. I
That
just
is
add
so-
it. No, I'll give you a
I mean, VS Code is
$1
very
so
pretty much.
you know it's hard. You make it, I give you 200. 500. Make it 500. 1 to 500.
This is my other.
No.
Let's make it. Just don't. Yeah, $1, $500. You can't make that. How about this? $5.
Yeah.
$5. You miss, you give me $5. I give you 1,000. No.
Yeah, but the now
I'll take 1 to 500.
I'll take
it. You give me the same odds. I'll take them. Alright, 1 to 200.
I mean, like, I don't know if
$5. $1. 1 to 200. $1. $1.
It could be going all the way down here.
Yeah.
Your top end.
No. I didn't
So
see
what I
it.
would do.
Like counts on the wall. So, wait, you want to take it? I'll give you. No, actually, that's scary. I don't want to do that.
Yeah.
No, you can say odds.
So it'll like make
Stop.
sure
You give me the same odds. 1 to 500.
Oh, so we have just take the
1 to 200.
No, that's like
I'm stupid. You guys did that on a coin toss.
no, it was 50-50. I'll do the 50-50.
So, random indicator variable. The $1 was random indicator. Not a stochastic. Indicator variable is random.
Oh.
House is closed.
Okay, let's finish the rest. So after 10,000 epochs of training, we are the loss is this small, and we still have those test examples reserved from 1 to 100. Let's see how it performs on how this FizzBuzz model performs on that. So you'll see it's 1 to Fizz4 buzz, Fizz7, 8 Fizz buzz. I have this final program to calculate the accuracy. So 98 of them are correct among 100 of them. It's not bad. It's 98% of accuracy. So that's it. Any questions about this mini project? I think the thing to remember is this kind of training loop. You define the batch input, batch output, and make the prediction, compute the loss, zero the grad, do the backward pass, and do the optimization. Most of the time, you just copy this framework and then change the model, then you're done. Change the model. Like this model is a two-layer neural network. And now, after we finish this project, or this notebook, I have another, there's another example about image classification. Let's just do that. Let me shut down this notebook. And then we will do a convolutional neural network for image classification. So we know what convolutional neural network is. Sort of. Let's first get the data. I'll use the MNIST data set to tensor. Because this MNIST is defined by PyTorch provides this pre-processed data set, so I'll just download from there. And let's see what those numbers are like. So this is the data set. Sorry, my computer is slow, especially when I'm broadcasting. So there should be 60,000 images. Each MNIST image is of shape 28 times 28. So it will be, this is one particular image. Dot shape. It's of shape 1 is the channel size. If it's an RGB image, it should have shape 3 times something. But this is a grayscale picture, so it only has one shape. I think I can plot it by matplotlib. Import matplotlib dot pyplot as plot. I'm not familiar with plot, so let me just see whether plot.imshow data 0, does that work? Okay, I want to plot it inline. So let's do that. What's the problem? Okay, I think I have to squeeze the first dimension. Does that work? Okay, this is a plot. So this is 5. What? Squeeze. Okay, for I in range 10. Let's plot 10 different images. Data I. I thought I should have 10 images, while I only have 1.
I guess I think the plot gets stuck while the image is displaying until
Okay.
you display the next one.
Do you know what I should do to? What?
I don't know.
Okay, never mind. Then let's just plot one image. Anyway, so the question is, what is squeeze? Squeeze is because this image has shape 1 times 28 times 28. So squeeze 0 means squeeze the first dimension out. So it has 28 times 28. and those are the images. And I want to do classification with.
So what are the images? They have 28 by 28, and they have the profoundness is only one number. So it's a 28 by 28 array.
Yes.
Matrix, and
Yes.
it's just one number, right? Which is the intensity.
Yes. So it's actually a grayscale image, but I think Matplotlib IM Show gives you this special color. So it's the color was not there. It's from this library. And we can design a simple convolutional neural network to do that.
Isn't that an oxymoron? It's a simple convolutional neural network.
What is the oxymoron?
It's a statement that is itself a paradox. Like
Oh.
convolutional neural network would never be simple.
Okay. Yeah, I get that. That's a joke. Okay. So it's a two-layer convolutional neural network. It has two conv layers. So we'll define conv1 and conv2. So the way we haven't seen this syntax before, but this is a way to define a model, a complex model with PyTorch. So you define a class, and the class inherits nn.module. nn.module is from torch.nn. nn is neural network, of course. So it's all the different neural networks in nn.module. It defines a module, and everything you define in init, if it's nn.something, then it will be considered as the model parameter. So these are the model parameters. You have two conv layers and two linear layers. And everything happen, all the things happening in the forward pass will be defined in the forward function.
Where you supered the word net.
Yes.
Which
So.
is I guess it's like this class.
Yes.
On a cell. Okay. But that still doesn't know that it's a convolutional neural network. It just knows
It's not. It's just a module.
Yeah.
So the only thing this class cares about is it's a PyTorch model. It has different parameters.
Okay.
So if you define, let's see. So these three lines are just boilerplate. You just copy that. Whatever model you define, so you always have those three lines. And then the following lines are the real model parameters. You have a convolutional layer. This means it's a 2D conv layer with from 1 channel to 20 channel. Because this is an RGB, this is a grayscale picture, so it's 1 channel to 20 channels. If it's an RGB picture, you might use 3 to 20, something like that. So from 3 channels to 20.
Channel, we talked about a class called depth.
I think it's usually called channel. Maybe depth is an older term, but it's just means 3 color channels or things like that.
Yeah,
Is it depth?
So we said like it was like a shape, right? And then it's the RGB and then how we talk about it.
Yeah. So if you anyway, I think you get it. It means just RGB different.
It's like the different channels don't share the same parameters. That's the
No, they don't share
Right.
the same
So
parameters.
the
Yes.
same thing with depth.
Yeah.
If you're at a different depth,
Right.
you don't have the same weights.
Yeah.
Okay, but then what do you consider when you do more than one example at a time? Because there's like, so channel is RGB, and then you also have like 1, 2, 3 images.
Yeah.
Right.
Yeah.
What's that considered? If it's not.
Can you ask the question again?
Sure. So we have RGB,
Yes.
which is like 3 channels of the same example.
Yes.
But then we also pass many examples together.
You mean different examples in the same image?
No, different images.
Different images.
Yeah. So
Then
normally you would think of like you do one, then another one, then another one. What we were seeing in class was like with the convolutional neural network, it doesn't necessarily do that. He might just send 4 examples with 3 channels each
yes.
through the network forward. So what's the amount of examples called? Yeah.
It's the batch size.
No, not even the batch size. There's like depth.
So why is that a problem? You are talking about different training examples. Why do you think if what's the difference between one example and 1,000 examples? The model is the model.
So when you do one example, you go all the way forward with one example and then
Yes.
all the way back. And
Yes.
he was not doing that. He was going forward with many examples at the same time and then going back.
By at the same time, you are still
So
doing
without-
forward
without
pass
updating
with
the
different
gradient.
times.
He's processing the second example without.
Oh, I
updating
see.
the
I
gradient.
see. So the gradients are just averaged among different examples. So you're still making, if you have 100 examples, you're still making 100 forward passes. But when you do backward pass, you have different gradients averaged. Each image will give you different gradients, of course.
Okay. Well,
So you
that's
just
not doing
average
less
that.
than that.
So when you're saying when you backward pass all, it's all, you take the average of all the gradients and
Yes.
backward pass?
Yeah.
Oh, okay.
In a batch. If you have 32 images, you average the gradients of that.
Okay.
If you have 1,000, you also get the gradient. So all my terminologies mostly come from the PyTorch documentation because they call it channels, input channels, output channels. And the second parameter is the kernel size. So this is input channel 1, output channel 20. Kernel size is 5. Do you guys know what kernel size is? It's the size of your filter. It's 5 times 5. So it always check the local receptive field of 5 times 5, and of course to the depth. I guess that's why you call it depths. The channels. So it always observe 1 times 5 times 5 local receptive field. So it's actually a local fully connected layer to the next layer. So it will apply. If you don't know that, CS2023N has a very good picture showing how it works. There is convolutional neural network.
So the filter gets applied.
This is the picture I'm talking about. This is how, if it's an RGB image, this is this kernel, this conv filter has size, so it has 3 channels, 3 input channels, and 2 output channels because there are 2 output. The parameter has steps 2.
Filters.
Yeah, 2 filters.
Okay.
I don't think it's 2 filters. It's called 2 output channels. 2 filters will be like 2 versions of this.
What are you saying? W0,
Oh, okay.
W1.
So I guess okay, then you're right. Then maybe it's 2 filters. But the output channel will be 2. Input channel will be 3. And
Input channel would be 3. Okay.
yeah, because you have 3 channels.
Input
Like
channel would be 3, but it would be whatever times time. So that's
yes.
in this case a 5 times 5, right?
Where do you get 5?
Because the zeros are just padding.
Oh yes, you're right.
So it's
Yeah, so it's 5 times 5. So 3 times 5 times 5 image. And you have your
2 outputs.
your conf layer has 2 output channels.
And the kernel.
Sizes are 3, yes. 3 times 3. They could be different, but mostly it's just this. It's a square kernel size. So now you have kernel size 5, and this one is, what is 1? Let's see. 1 is stride. So stride means you move the position by 1. Because it could be 2, then you jump the position. You pass 1 position and jump to the next local receptive field. Now you have conf1, and in the forward pass, you will use those parameters. If you never use those parameters, then they're useless. They will never be updated anyway. So in the forward pass, you first apply conf layer conf1. So without padding, you can imagine what happens here. With this picture, you see that with a 5 times 5 image, if the padding is okay, I think they have stride of 2,
Yep.
so that's why they jumps it. But if we consider the stride is 1, in our case the stride is 1, then your 28 times 28 image will becomes 24 times 24 because it's 28 minus 5 plus 1, so it's 24 times 24, and you have 20 channels. And I write all those shapes here. Yeah, question.
So if you have 2 filters, is that in the same layer or is that 2 different layers?
It's the same. Let's see it. It's actually a 3-dimensional fully connected layer. So your input is 1 times your input is 1 times.
If there's 3
20.
channels, I get that.
Yes,
So I
yes.
get that it's 3. It's like 3 parallel networks
Yes.
almost. But then
Oh, they're the
you
same
have
layer.
2
I would
filters.
say they are the same layer, because they are just
2 filters on the same
yeah,
layer.
yeah. Yes, because the images have 3 dimensions, so it has 3 different directions. So it's
So I guess what's the point of the second filter, like on the same layer?
you might imagine different filters are detecting different things.
Right.
Like the first filter might be detecting edges, so the second filter might be detecting some other features.
And what's going to determine that difference is going to be the random weights with which they start?
I think so. That's a philosophical question, or maybe not. There are some visualization techniques. I can't answer.
If they start with the same weights, then they would be identical.
Yeah, I don't know. I don't know how they end up with different features, but that's just a practical observation. They end up with different weights, and those weights usually represent different features of a local receptive field. Now this is the shape. Usually when I code, I write down the shape so I don't forget what I'm doing. And then max pool 2D of kernel size 2 times 2 means every 2 times 2 box you get the max. So originally it's 20 times 24 times 24. With that you got 20 times 12 times 12 because the shape is reduced by half, both the length and width.
Possibly draw
Yes.
towards the
I think is there a max pooling? So this is max pooling. The original shape is 4x4, and for this 2x2 matrix, you get the max.
Oh, I get that. I'm just saying even the structure of the simple quote unquote network that you're writing. Right?
Oh.
It starts with 1 times 20. Like, what does that mean again?
So it will be like, let me try to draw that. I don't think I can draw it very well, but originally it's 28 times 28 with only one channel. This is one channel, and after convolutional layer, it becomes slightly smaller because it's 24 times 24. But now it has 20 channels. Just drop some channels here.
Each of those channels have their own weights, right?
Yeah, they have their own. I won't call it. So by weights, you are talking about the parameters of the model. These are the more like intermediate representations of middle layers, the hidden states. Because we usually, when we say weight, it usually means the parameters of the network, the conv layer.
Okay.
That 20 times 5 times 5, those are the weights. And these are the more like the hidden states.
Why 20 times 5?
Because you have 20 channels, right? All 20 channels have different parameters.
The weights go between 24 times 24, right? To 5 to 5?
Your 5 times 5 parameters will be applied to all those local receptive fields. You only have one version of the conv parameter.
There was 3 channels.
In this case, there are only one, because I'm working on MX.
Sure. So where does the 20 come? Why is there 20 channels?
20 is defined by myself. I have 20 there. Because I'm talking about my particular example. So it's 20, and then it becomes 50. So let's just go back to my code. So now this is 24 times 24 times 20 channels, and then we do max pooling by half. It has 2 kernel size and 2 stride size, so you have a half image. Still have the same number of channels. So this is 14. This is 12 times 12 times 20. And then you do conv again. But that's conv 2.
Okay, but before you go to that,
Yes.
so what's the images on the left, right?
Yes.
Is
is the image.
What's the size of those edges?
These are like 28 times 28
Okay.
times 1.
I don't see a 28 anywhere.
Because it's defined in X. You don't need that in the model.
You
The
don't-
model, why does the model need to know the image size? The model needs to know the image size, but it's not a model parameter, right?
20 to 20 is the original picture
Yeah,
size, right?
This is the picture size.
Then it converts to 24 by 24 because every image will be the 24 by 24 sample size for the next class, next channel. Then
So-
each channel has 24 by 24. That's what the next one is.
I think you might be confused with the
So if you
input.
gave it images that were 100 by 100, it would still work.
It will still work, but you will get something you don't want eventually. You will get an error at this here. You won't get an error here. This is fine. This is fine. This may be fine. This may also be fine, but you will get an error until this point.
So
Yes.
what exactly are you passing in for X?
X is the image.
Image, okay.
Yes. X is a 1 times 28 times 28.
Okay. So now you're transforming one image
Yeah.
into 20 filters of 24 by 24,
Yes.
and that's the different the zones of the image.
Yes.
It's not gonna. Each layer won't have the same input. Some of them will have similar input. Some of them will have shifted input. Right.
Correct.
So in the model part, all the things you define here are the model parameters. You don't care about the image. You can
To me,
define
the
it.
input layer is still part of the model. Like the fact that you think it's not is okay.
I don't think it's a part of the model. This is not a part of the model. This is not a part of the model. These are just the intermediate representations of prediction. They are, by model, I mean all the parameters you're going to train. You won't be able to train these things. These are just the data.
But the number of model parameters you have depend on the sizes of those things.
No, it doesn't depend on any of those. Okay, I see why you I see why you say they dependent on those things. But actually they only depend on those things. These 20 or 5. Those numbers. It doesn't depend on so I see why you say it depend on that, because this 4 times 4 comes from the image size. But
I'm
only
saying
the
even not the image
size.
size. You pointed at the filters intermediate. I'm saying there's going to be thetas that are associated between moving between those intermediate layers to the next ones, and the shape of the thetas.
Yeah, the thetas are just comp 1 and comp 2, right? What other thetas are you pointing to?
So the weights.
The weights are just comp 1 and comp 2.
You said the number of channels was 20.
Yes, 20 is
So if the
defined
number
here.
of channels is 20, then you're going to have weights associated with each of those 20 channels.
Yeah, so
So
all
it
those weights are
does
there.
affect the model.
So all those weights are here. So there is a, if you're talking about that, there is an inherent kernel here.
Like whether
This
I
is
say
20.
there's 15 channels or 100 channels, I get different weights.
So
I
these
get
are
different
the-
model.
The real parameters are here. There is a 25 times 5 parameter. These are the parameters you're training. Those things are
The data.
the data. You'll back propagate through that, but you won't be updating any of those numbers. You only update these parameters. So this is max pooling. You don't have any parameters. Max pooling is just max pooling. And then you will do conv2d. In conv2d, you will have a 20 times 50. I don't even know how to draw that because it's a 4D. It's a four-dimensional thing. But there should be some parameters here. And you will convert that to be a shape of 20 times 8 times 8. So this will be 8 times 8 times 20. 8 times 8 times 20. And you do max pooling to D. It becomes 4 times 4. Sorry, it should be 50, right? Because it's conv2D. And then you still have 50. This is 50, 4 times 4. Any questions about that? So you're just increasing the channel size from 20 to 50 from this step, and you do max pooling, reduce the image size. And finally, we just define 2 fully connected layers.
Where does 8 come from?
8.
Yes.
8 comes from 12 minus 5 plus 1.
Oh, right.
So that's all. That's everything about the convolutional layers. And then finally, you have 2 linear layers, because in the final picture we have 4 times 4 times 50 neurons, and then you have a fully connected layer from this many hidden states to 50 hidden states, and finally it's 500 to 10. 10 comes from 10 different classes, because MNIST has 10 classes. So you want to make 10. You want to predict 10 logits, and the logits of the maximum position of the logits will be your prediction.
Is there any particular reason why you chose this number?
These parameter size,
Yeah.
that I copied it from some other people's code. So I think a lot of people have tried different parameters. This must be one of the good settings that you can easily get
I
good
don't see
results.
24 there either. I don't see 28. I don't see 24.
You don't need to see 20. Why do you say you don't have? You don't see? Do you mean you don't see 24 in the model?
Yes.
Because you don't need 24, right? This is the image size. It's coming from X. Of course, this model won't work for an image of different size, but you kind of specify that in 4 times 4.
So is this working like this way? So you have 2 linear levels of
Layers. Yes.
layers, and
Yeah.
then you have the forecast layer, and then you have another forecast layer. So basically, you have 4 layers technically.
Yeah, they are 4 layers. You can
So
say it's
then
4 layers.
after convolution 2, you're using the output 4 times 4, 50 as input,
Yes.
and transfer to the 500 different signals
Yeah.
on the forecast 1, and then you forecast to translate that 500 to the 10 decimal or 10 class you try to
Yeah.
softmax.
So it's like you assign scores to 10 different classes, and the highest scored one will be your prediction. And you optimize that by cross entropy again. This is just a different way of writing cross entropy if you think about the math. I first do softmax, then do log. And the reason why I write log softmax is because it's more numerically stable. If you do log softmax, you will get some kind of weird errors like NaN or very big numbers. I don't know if they fixed that, but in some earlier versions of PyTorch, you can easily get those kind of numerical unstable results. So we will, let's just, because the time is almost up, let's just show how this model works. So you have MNIST data, and I think I've already get all the data. And I'm going to do one step of pre-processing. I will get the mean of all pixels and get the variance of all pixels. And I will subtract the mean of the pixel on every position and divide by the variance. That's like a normalization step to convert that into a standard normal distribution. And sometimes that helps. So in the homework assignment, you can also try that. I just compute the mean and variance. And then where is my data set? Okay, these are my train and test and evaluation loops. You will see the train loop is very similar to what we did before. You enumerate on the train loader. The train loader is from, it's actually provided by, okay, it's not here yet. But you get the data and the target. The data is a 1 times 28 times 28 image. And it has a batch size of something. And the target is from 0 to 9. So you have these 2 input. And you use the model to make the prediction. And you do negative log likelihood loss of the prediction. The prediction will be of shape batch size times 10, because the model just defines the last layer would be of size 10. And target, what this NLL loss does is that it will pick the value from that particular index of the target index. If target is 5, it picks the 5th log likelihood. And yeah,
One question. So the step where you softmax at the end
Yes.
gets the actual label, I think. What's the point of that?
The point of that,
Instead of like just taking the max probability. So okay, you output like a vector of probability.
Yes.
Right? And like also in the homework, they say, oh, like you can use a soft max if you want. But I guess why use an extra calculation step if
I
you
see.
just choose the max?
So the reason is, let's see, what's the reason? But this is more for the for optimization concern. Because
there's
you-
only 10 digits that you try to forecast, 0 to 9. You try to predict which one is most likely.
I guess his question is, why do you do softmax instead of just do argmax? Is that
Yeah,
what you
that's
ask?
what I'm saying.
Yeah.
Why don't you just use
Why do you do soft? That's one reason, but
you
it still
already
doesn't
have
answer
the
that
problem.
question. So
You don't have the problem. You have the isolated probabilities, as if the rest of them didn't exist, right? If you add up all your probabilities, it adds up to much more than one.
Right. Yeah, because it's 0, 1 for every label.
I still don't know why you would use softmax, but I'm just saying it's not just the probabilities that you get. I don't know.
So the reason is more for optimization, because you have to guarantee that the loss is a positive term. If you don't do that, you won't be able to compute the not. It's just the math of negative log likelihood. As I have shown before, I closed that window, but it's the log of the softmax of something. So that's why you do that. So this term will always be positive. If you don't do log softmax, this term could be negative. So I think that's one reason of doing that.
It's just like e to the minus inner product over the e to the sum of all the different inner products for all the different labels, right? That's the softmax.
Yeah. Because if you don't do that, then those logits could be negative numbers or whatever numbers. They could be very weird numbers. So you can't do optimization on those numbers. It's mostly for this optimization technique. And then you do zero grad backward and optimization, and you compute the loss.
Up to 0.
Yeah, zero the gradient. So train and test. Oh, the other thing I forgot to mention is that when you train a model, it's a good practice to always write model.train before you do gradient descent. And at test time, you write model.eval. The reason is for some layers perform differently on training and testing. For example, dropout or batch normalization. They have different, the equation is different in train and eval, so you have to specify that. Otherwise, you will get some strange errors. And at test time, wrap it by with torch.nograd. It means do not compute any gradient when you perform those operations. This will save you a lot of memory. If you don't do that, you can easily get out of memory error with that. So I won't train it again because it takes a while. But you just provide the training and test data, and it's just standard optimizer of stochastic gradient descent. And let's see what else. And you use cross entropy loss. It's written there, or called negative log likelihood. The accuracy is the accuracy I got is 98.34. So in homework 5, you're gonna train on fashion MNIST and Cipher 100. So it's a 10-way classification and a 100-way classification. I believe in the first example, you can directly use my code here, and that will give you reasonable well predictions. But you can always tune those parameters, or you can even add an extra layer to see whether you can get better performance. But this is a good starting point. I have posted everything on my GitHub. Yes.
Because in this thing, right, if we just give it a different pictures of different size, it'll break, right?
Yes.
So I guess why wouldn't we write a general case where like you could just automatically adjust
the image size?
Yeah.
I think from what I've seen, people usually do that as a pre-processing step. You convert your image to a certain size and use that as input. If it's not 28 times 28, then you find a way to convert that. Either you just crop a region from the image, or you can resize it.
No particular, just how we usually go about it.
From what I know, I don't think there's a universal way of getting the input from a random image. Because if it's a huge image, then you can't do anything to make it 28 times 28. Yeah, you can search online to see what other people say about it. Because I'm not an expert on image, on vision stuff. But some good tricks I know is do this kind of normalization. Normalized by this is mean and this is standard deviation, which I calculated before. And sometimes that helps. These are from, this is from PyTorch. PyTorch Vision. Torch Vision has this function called transforms. TensorFlow has similar features available for you to deal with image data. But there is very little you need to know about it. Even if you don't do this transforms, it's still fine. You don't have to. And you can always do it by yourself. Just convert NumPy to a tensor and do all the remaining stuff. And even for this normalization, you can do it by yourself. Just subtract the mean and divide by the standard deviation. Let's stop here, and you can go if you want. And I think I can spend 5 more minutes here, and then I need to go as well. Sure.
Is the midterm, well, do you know if the midterm is also on?
I don't know anything about the midterm. I think you have to ask Amitabh.
Probably yes. So, I wanted to ask for some help on troubleshooting my neural network.
Okay. I probably won't have time to do that. How about you set an appointment with Amitabh? He mentioned that if you ask that, he can help you on that. Yeah. Because you posted a question. You posted on Piazza, and he said he could help. I'll stop